Hi, and welcome to lesson 77B. Today we're going to be exploring the exponential decay function. We will be looking at examples that involve percentages, just like in the previous lesson. Okay, getting started with the exponential decay function. It's just an exponential function. And still the A represents the y-intercept or the starting when x is 0, time of 0. Okay, just like in the exponential growth function. But instead of writing the b, hold on, the factor of change now is going to be a number that is less than 1 because it's going to be decay. So because we're going to be looking at percentages, we're going to do 1 minus the percent of change. So the 1 still represents 100% of what we start with, but then we're going to subtract the percent that we're losing or decaying. And of course, then the x is still going to be the time periods. So if you need to pause the video to write this down, please do that because it's going to be really important that you have this in your notes. Okay, and then when you're ready to continue, we can move on. All right, here's our first example where we're going to see a percent of decay or a percent that's being lost. Here we have Mr. Math. He's losing 20% of his hair each year. So there's our loss of 20%. I'm just going to underline that. Losing 20% of his hair every year. If he currently has 1,546 hairs on his head, about how many hairs will he have left after 10 years? So you can see that this is, because we're losing hair, this is going to be a decay. All right, so let's start with our function, y equals. Now our a value is going to be our starting value, our time of 0. And he counted, because he has so much time on his hands, 1,546 hairs on his head. Oof. All right, big parentheses, because we have to start with 1, which is 100% of the hairs on his head, and we're to subtract the percent that he's losing. And so it's 20%, so go back up to the 20%. Here's the decimal point. Back it up, because remember we have to change it to a decimal. So 0.20. And then the x, the time periods, is going to be, well, if he's losing 20% of his hair each year, how many years is this happening for? And that's happening for 10 years. So our exponent is going to be 10. How much hair will he have on if this loss continues for 10 years? Now, don't type anything into your calculator yet. Let's simplify what's going on in the parentheses. And trust me, this is going to be really helpful for later. Okay, so in here, 1 minus 0.20. Think of this as money. If I have $1 minus 20 cents, that's 80 cents. Or if you need to use your calculator, you can do that too. It's 0.8 or 0.80. It doesn't matter if you put the annex 0 on there or not. And then to the 10th power. Now, what I want to point out here is that this b value is less than 1. That's what makes it decay. Remember, numbers less than 1 are decay. Now go ahead and just type it into your calculator or do order of operations, and we're going to figure out the approximate hairs on his head. And if you round this to the nearest whole number, about 166 hairs. Sorry, Mr. Math. You are going to be bald soon. Very few hairs left on your head. Okay. Let's try another one. Here we've got a car depreciating in value. We talked about a house appreciating in the last lesson. Cars lose their value typically. Now, not collector's cars, but a typical car that you drive on the road every day is going to depreciate or lose value as it ages. So here we have a $15,000 car at time of 0 when we bought it. It depreciates in value 8% every single year. So part A is just asking us to write an exponential decay model for the value of the car after just X years, any number of years. So we're going to use X. So just very basic. All right, let's start with y equals. If it's a $15,000 car, that's the A value. Big parentheses. So I have a 1, that's 100%. Remember, 1 as a percent is 100% of the 15,000 that we start with, and then we're going to subtract 8%. Now go to the 8%, decimal points here, back it up, back it up. We want to change that percent into a decimal, so 0.08. And then to the power of x. Okay, because I want us to write after x years. Now stop right there. In the parentheses right here, 1 minus 0.08. Let's simplify that. So think about if I have $1 and I subtract 8 cents. What would that be? Well, that would be 92 cents, right? So I'm going to erase this. You maybe just want to rewrite. So 1 minus 0.08 would be 0.92. Now notice that this number is less than 1, making it a decay. All right, so let's go to the next part. And the next part's going to give us a situation now where we want to apply this function rule that we just wrote. So use your model to find the value of the car after 7 years. So let's figure out the value after 7 years. So now we actually have a time period that we're going to be plugging up there for x. So we got y equals 15,000. In parentheses, remember 1 minus 0.08 was 0.92. 0, I'll go 0. 0.92. And now I'm going to put 7 as my exponent because it's decreasing 8% each year, and I have 7 years that I want to do this. So I'm just going to type this into the calculator and figure out what the value of the car is going to be. So thinking like 8,367. And if you look at the decimal, I think it's like 0.699, which would go up to about 70 cents if we rounded it to the nearest penny. So this is what the car would be worth after 7 years. So it started as a $15,000 car. It lost a lot of value after that first 7 years, and this is what it's worth. All right, great problem. All right, on number 3, we got beetles. Don't you love the picture? It almost looks like he has like a horn right here going on. Very interesting. All right, a large population of 2,200 beetles are infesting your lawn. Oh, great. Now we got beetles. Before it was termites eating our foundation. A population of 2,200 beetles are infesting your lawn. You decide to use a spray that will eliminate the beetles at a rate of 5% each minute. How many minutes will it take to eliminate all of the beetles? Wow. Okay. Here's our starting value of beetles. We are eliminating them at a rate of 5% each minute. How many minutes is it going to take for them to be gone? All right, exterminators, let's write a function rule for this. Y equals, we're going to start with 2,200 beetles. All right, we are decaying them. They're dying. 1 minus 5%. So remember decimal, back it up, put the 0 there, 0.05. And then the exponent is going to be the time periods. So we're asked how many minutes? Well, I don't know how many minutes. So we're actually trying to find this x. Okay, before you start plugging in these multiple choices that you see over here, before you do that, let's just simplify. Okay, so what I want you to do is just to see if I can get this erased here. It doesn't want to erase. Okay. This part right here. So we got 2,200. Think $1 minus 5 cents would be 95 cents, 0.95. X. This is going to be helpful too when you type it in your calculator. Okay, and again, just pointing this out again. Now you're getting sick of it probably, but it's less than 1, so it's decay. All right, so now you have some choices. You have different choices that you can plug in here for minutes. All of these different possibilities, plug them in for X and see what's going to eliminate the beetles. Now remember I had mentioned, I think it was lesson 7.6, that when you have exponential decay, it gets really, 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 really close to 0, but never actually touches 0. So you are not going to actually see this become 0 beetles. So as you're trying those numbers, we're not looking for 0 beetles. But if we can get this less than even a beetle, like the last beetle is just dying, that's kind of what we're looking for here. So if you're plugging in, if you even tried A and you're plugging in A, you still got beetles left. So that means if you have waited 101 minutes and you still have beetles left, you're still going to have beetles at 95 and 87 minutes. Try 151 minutes. Try plugging in the exponent 151. So right here, let's make this 151 and see what happens. Type that into your calculator. Now, do you notice, I think I'm still on eraser or something. There we go. Okay, do you see that your calculator is going to say like approximately 0.95? Like not even a beetle. That's not even one. That's less than a beetle. That one last beetle is like dying. It's not, it's not going to be here for much longer. So the best answer choice here would be 151 because you have less than a beetle left. Remember, with exponential decay, it's going to get really close to zero, but not actually touch it. So 151 would be the best answer choice for that one. And again, that's just process of elimination. Okay, number 4. Now, I've been pointing out the B value showing growth or decay in a lot of the examples today and yesterday. So let's see if you can tell just by looking at the function if it is exponential growth, decay, or neither. So we're focusing on the B value. That's going to be telling us if this is growth, decay, or neither. And what do you notice about this number? It's less than 1. So what does that tell us? It tells us that it's going to be decay. Okay, we're multiplying by a third, and so that's going to be the same thing as dividing by 3. So let's go over here. Oop, shoot. I accidentally clicked, and now you can see the answer to this one. Oh, well, that's okay, though. But here, why is this growth? Well, hopefully you can tell me that because this number is bigger than 1. It's 1.075. That would actually be 7.5% growth. So that because the number is bigger than 1, it's growth. Okay, let's go down here to this one. 5 halves. Is it growth or decay? Well, 5 halves, yeah, it's a fraction, but the fraction is bigger than 1. It's actually 2.5. So that's going to be growth because it's bigger than 1. All right, then this last one. It's exactly 1. Now, I've been telling you that if it's bigger than 1, it's growth. And if it's smaller than 1, it's decay. But what if it's exactly 1? I bet you've been wondering that. Well, if it's exactly 1, then it's neither growth or decay. It's not either. But let me show you why, because you might be wondering like, well, why is that? What do you mean it's not growth or decay? Well, let's take a look. In order to explain this, I'm going to kind of pop up a graph and a table here. Okay, if I were to make a table of values, if I were to plug in 0, 1, 2, and 3 up here into the x for the input, and if I were to make this table of values, so if I plug in 0 for x, 0 times 1 to the 0 power is 1, my output would be 3. If I plug in 1 as the exponent, 1 to the first power is still 1 times 3 is still 3. If I plug in 2 as the exponent, 1 to the second power is still 1, and when you multiply it by 3, you get 3. And if I plug in 3 as the exponent, 1 to the third power is still 1, and when you multiply it by 3, you get 3. So do you notice how the output value stays the same? 3, 3, 3, 3. It stays the same. So if I went over to the graph and I actually graphed these points, 0, 3, 1, 3, 2, 3, and 3, 3. It's a straight line. It's not showing exponential growth, which looks like this, and it's not showing exponential decay, which looks like this. It is showing neither growth or decay because the B value is 1. Okay? So if it's greater than 1, it's growth. If it's less than 1, it's decay. If it's exactly 1, it's neither growth or decay. All right. Now this part gets tricky, and I mentioned this in the video lesson from yesterday, 7.7a. It's a lot easier to determine the percent of growth than the percent of decay. So I'm going to show you a strategy for this. So I'm asking you, looking at this exponential function right here, what percent of decay is it showing? And maybe your first instinct is going, oh, this is 70%. It's not. Let's take a look at where this came from. It came from 1 minus, right? So think of this as money. This is like 70 cents, right? So if I take $1 minus what would give me that 70 cents? That'd be 0.30, wouldn't it? So I had 100% at that 35 where we started. I subtracted a 30% decay. And then remember, this would have been in my parentheses, and I would have simplified it to get the 0.7, right? So this came from a 30% decay. So I kind of have to work it backward a little bit. So 30%. Try the next one. Starting with this, right here, this is our decay. It's less than 1. Think about where it came from. It came from 1 minus, right? That's what was in the parentheses. Think of this as money, 0.25, 25 cents. So a dollar minus, when this had to be 0.75 for you to get the 0.25 when you simplified? Yes. And then this right here would have been the percent that you changed into a decimal. So it would have been a 75% decay for you to change it to 0.25 after you simplified it. So it'd be a 75% decay. So the decay are a little bit trickier. You really have to think about, where did the B value come from in the problem? What was being subtracted? Okay, and then on to our summary. Again, here's that exponential decay function where we were seeing 1 minus the percent. If you didn't get a chance to write this in your notes, you can go ahead and pause the video and go back to the front of your notes and write it in there. Thank you so much for joining me. Have a great day.